As chair of the Knuth Prize Selection Committee, it's my pleasure to introduce this year's winner, Avi Wigderson. And first, before saying more about Avi, let me also thank the other members of the selection committee, Alan Fries, Shafi Goldwasser, Noam Nissan, Ronit Rubenfeld, and Andy Yao. So now about Avi. So Avi has been a major force and guiding spirit for theoretical computer science for many years. His work revolutionized our understanding of randomness in computation. In a series of results, he showed under widely believed computational assumptions that every probabilistic polynomial time algorithm can be fully de-randomized. In other words, that randomness is not necessary for polynomial time computation. This was achieved by a series of papers of his, starting from the paper Hardness versus Randomness with Noam Nissan, and culminating in a paper with Russell and Pagliazzo, showing that P equals BPP is implied by the assumption that there are functions that can be computed by exponential time Turing machines that cannot be computed by sub-exponential size circuits in the worst case. And to this day, this is one of the strongest pieces of evidence we have that P equals BPP. In cryptography, in two landmark papers, one with Goldreich and Macaulay and one with Ben-Or and Goldwasser, he showed how one could compute any function securely in the presence of dishonest parties. Avi also, with Goldreich and Macaulay, showed that all problems with short proofs, in other words, all problems in NP, in fact have zero-knowledge proofs, that is, proofs that yield nothing but their validity, essential cryptographic construct. Additionally, originating from cryptography, but with applications to many areas in theoretical computer science, Avi, with Ben-Or, Goldwasser, and Killian, defined the model of multi-prover interactive proofs. This model for the first time showed how it would be possible for a polynomial time machine to verify an exponentially long proof. This idea had substantial impact. Among other things, it led to the celebrated PCP theorem and the avalanche of follow-up works on hardness of approximation. In the area of parallel computation, Avi provided a series of foundational results about parallel computing models. This includes the first RNC algorithm for constructing a perfect matching in a graph with carp and upfall, the first NC algorithm for finding a Maxwell independent set in a graph with carp, and a number of foundational lower bound results. With Reingold, Vadan, and Capalbo, Avi gave the first efficient combinatorial constructions of expander graphs. Before this work, only algebraic constructions were known. These combinatorial expander constructions enabled a series of important subsequent results, including Reingold's deterministic log space algorithm for ST connectivity. In addition to specific research results, during his academic career, Avi has supervised a large number of postdocs and PhD students. He has written many expository and survey articles, such as the award-winning survey Expander Graphs and Their Applications, and he recently published the book Mathematics and Computation. And with that, let me welcome Avi. Thank you.
Thanks. Okay, let me test this. Yeah, it works. Thank you very much, Avrin, and thanks, everybody. Guys, there are plenty of seats here in the front, if you want to sit. I'll talk for an hour, so if... all right, so yeah, I got a title to attract you all. It's a sort of non-trivial question what to focus in a talk like this, but as usual, I cannot resist myself and just focus on things I want to teach you on. Basically, it will be mostly technical, so that's a warning. And I also cannot resist, talking about propaganda for our field, just, telling you how great it is. So there'll be a sprinkle of this in the beginning and a sprinkle in the end, and most of it will be the story that these connections of optimization, complexity, and math. I think I'll take my other glasses and see the screen better. I think they could have afforded another screen in the middle here. Okay, so just to clarify, this is my view of our world of theory. I believe it is a central, independent academic discipline. By now, I think we understand it extremely well, with important interconnections going back and forth to all these other important disciplines. And whenever I show a slide like this, I and probably you also think that anybody, even with my limited PowerPoint capabilities, can put something else in the center of the universe. And so, in fact, it's, as you know, it's a long human tradition to put yourself in the center. I mean, that's, this lasted despite I don't know, 1,500 years of evidence, it lasted. So basically what it means is you have to give arguments. You have to believe it, first of all. For this, you have to learn and understand about your field and about the connections. And if you are convinced of that, my point is that then you should educate. You should convey to your students, to your colleagues, and to the general public. So I'll talk a little bit more about these connections at the end, but I want to focus. This talk is mainly about connections of theory to math. So I'm going to talk mainly about, at least start or demonstrate these connections first with one problem and one algorithm. The problem, I'll define everything. The problem will be singularity of symbolic matrices. The algorithm will be alternate minimization. And then we'll see where it rolls. And we'll see lots of connections and applications in math, physics, and computer science. And I think you'll see how it rolls really captures what's been happening in this research I've been doing with these collaborators listed in the title slide in the past 4 years. It seems, it really feels like there's a snowball that starts at the top of a mountain very small, and it starts rolling, and then it seems to be picking up lots of stuff and lots of information from many different disciplines. So there's a lot of learning experience that happened for us here, and of course, discovery process. So I want to tell you this story. And the other part of the story, which is, I think by now we are, in this community, we know lots of interconnections between things that may be not so obviously connected. So let me start. This is just a list of some of the areas that will be related to these two problems I mentioned. And you just look at them. You don't have to read the small print, but the big print: non-commutative algebra, invariant theory, quantum information theory, analysis, and of course computational complexity and optimization. For me, you can guess that it started from trying to prove lower bounds, and the optimization part, which is not, I don't do so much, grew on me, and there are just wonderful connections. In particular, hopefully we'll see at the end that this research in particular enables to solve very general families of things that we didn't know. Some quadratic systems, polynomial system of equations, and some families of exponentially large LPs in particular. So I want to describe this one problem and one algorithm. So let me start from the problem. And it had a long name, so before that, we'll start from a baby version. And this will also be carried throughout the talk. And the baby version is nice because you all know it. This is a problem of perfect matching. So eventually I want to talk about the problem of singularity of symbolic matrices. This is the baby version of it. What is bipartite matching? You know what it is. You want to give your kids candies, but not all of them, they each like a subset. So you want perfect matching, and this particular graph has one. So it's possible to match a candy to a kid, whereas some graphs don't have it, like this one. And one important theme is taking a combinatorial problem and attaching some algebraic structure to it. Often it helps understand it, and we know how to do this too. This adjacency matrix of the graph G. And we can understand the existence of perfect matching in the graph by looking at a polynomial over this matrix, and you know what it is. The graph has a perfect matching if and only if the permanent of the matrix is 1, where the permanent is this formula written there, which is, I think the whole point of pointer is lost, right? There is no, I have nothing to point to. The permanent is like the determinant without the signs. So just summing over all diagonals and taking the product of the entries. This problem, perfect matching, has a polynomial time algorithm, which many of you teach, and the other few have learned recently. The augmented path algorithm, I think you know that this algorithm already dates back to the late 19th century. Jacobi, in work on partial ordinary differential equations, discovered it, because like many mathematicians who discovered algorithm, he simply needed to get himself out of an exponential, obviously exponential exhaustive search. But anyway, we have a polynomial time algorithm for this problem. However, we also know that the permanent is not a friendly polynomial. And here's an ingenious algebraic connection that Edmonds came up with, which is different than this one. And it's the following. Edmonds said, suppose, just 50 years ago exactly, suppose instead of ones in the adjacency matrix, you put variables. So for, if there's an edge between ui and vj, you put xij, a variable. And if there's no edge, you keep it as 0, okay? And the observation is, so that's now a matrix of, a symbolic matrix. And the observation is that now the graph has a perfect matching if and only if the determinant of this matrix, the determinant, something much friendlier, is not identically 0 as a polynomial. And this is, sort of obvious because if there's some monomial corresponding to a perfect matching, all variables are distinct, nothing can cancel it. So even though there are minus signs in the determinant, there is no problem here. So, okay, that's an observation. And I would say the leap that Edmonds made was, this is a problem in P because it's equivalent to perfect matching. But the leap that Edmonds made was saying, well, let's now, instead of putting, we have a question, we have a special case of a question, let's generalize it. Let's say that we are given a matrix, every entry has a linear form in some set of variables, and we want to know whether the determinant of this matrix, which again is a polynomial in these variables, is identically 0 or not. Okay? So let me specify exactly what's the input to this problem. If you have a matrix of linear forms, one way to write it is to write the matrix coefficient of every variable. So really the input is just a bunch of matrices over your field. In our case, we'll mainly worry about the rationals. But anyway, you are given a bunch of matrices. And I ask you whether the linear combination with formal variables, when you evaluate the determinant of the symbolic matrix, is identically 0 or not. And I'll call this a problem Sing for singular, the singularity problem. And this is a problem of singularity of symbolic matrices. So now it's not obvious how to solve this problem in deterministic polynomial time. And that was his question. And today this question is open. In fact, the main problem that we wanted to solve, still want to solve, and looking for your help. But a lot of interesting things happened with it. First of all, Lovaas observed, this was the 70s, was the time of probabilistic algorithm. He noticed that there's a fast probabilistic algorithm for this problem. You just plug in random numbers into your variables and evaluate the numeric determinant. And that's, of course, if it was identically 0, you only get zeros. If it was not, probability of hitting a 0 is tiny. So that was simple. So we already have an efficient algorithm for this problem, but it's probabilistic. More things happened. The same year, Valiant showed that this problem is important. So, so far it looks like, okay, it's a problem, but its importance grew. So the first thing was that Valiant discovered that this actually captures, completely captures all algebraic identities. all algebraic identities in all algebra books, in all, of mathematics, all over. They are all in formulas, so they all can be captured by a symbolic determinant. That's what we call PIT, polynomial identity testing. So it's somehow universal for algebraic identities. All algebraic identities can be verified in this way if you had an algorithm for them. Turns out that mathematics is littered with special cases of this in various fields, modular isomorphism, graph rigidity, and so on. But I would say that the sort of the killer proof of the importance of this problem came when Cabanet and Impagliazzo proved this result. So for those who didn't see it, it should come out. Yeah. I hope you'll be duly impressed. It says the following. We already have a probabilistic algorithm for the problem. But if you have a deterministic algorithm for the problem, efficient deterministic polynomial time algorithm for this problem, then basically you prove P different than NP. Or more formally, you proved VP different than VNP, which is the algebraic analog that I will not define of P versus NP. And even this is in quote because it's not exactly what you prove, but basically you prove a significant major lower bound. That's what will happen if you find just a deterministic polynomial time algorithm for this very specific problem, okay? And, this is exactly the, it has de-randomization in it, has lower bounds in it, things I really love and invested lots of years on. And that's what we will try to solve, and we will fail, but as we fail, we'll do other things. So we'll do what we always do when we want to solve a problem we can't, and we just change it, right? So be honest, guys, very important for your career. So I want to tell you about the dual life of symbolic matrices. So again, here's the problem, as I stated it. You get a bunch of matrices, and you ask whether this symbolic matrix is singular. So I want to call it singular because as we talked so far, I'm sure you assumed, like I did, that these variables commute. In the commutative case, the same question to ask whether this matrix is singular over the function field over these variables and whether its determinant is identically 0. And we know, this is what we know about it. But let's change the question and let's study it in the non-commutative case. So ask whether this matrix is invertible when the variables do not commute. And now it's not even clear what it means. And in fact, it's a non-trivial thing to define what it means. But there is, I will not define it formally, but there is an analog of the field of rational functions in the non-commutative case. It's much harder to define. It's a much weirder object, but it's formally defined. And we ask whether this matrix in symbolic non-commuting variables is invertible. And this turns out to be a really interesting story because it seems like a much harder problem. Even, unlike the other, even showing decidability of this problem was a major thing, was done by Kohn. And people started looking for good upper bounds, and the best was an exponential time upper bound by Kohn and Rettenauer. So it looks harder, and this is the main thing I want to tell you about in the first half of the talk, is that we have a polynomial time algorithm for this problem. We'll also see why it's interesting later, but I sort of hinted in the beginning about all these connections. Anyway, there is a polynomial time algorithm for this over the rationals or over infinite fields, and soon after, Ivan Yoskiao and Subramaniam came up with the polynomial time algorithm, very different one, algebraic one, for practically any field, any large field. I will talk about the work with Gar, Gurwitz, and Oliveira, and this algorithm will be, as you'll see, despite the algebraic nature of the problem, will be analytic. So I want to talk about, so far so good. Okay, so this is a problem of, what we want to solve is we get a bunch of matrices describing a symbolic matrix in non-commuting variables. We want to know whether it's singular or not. Now to the algorithm. What kind of algorithm is going to be used in the solution of this? Again, I'll demonstrate it on our baby version on bipartite matching, and then we'll see the generalization to this. Okay, so the algorithm is alternate minimization. Many of you know it from machine learning, statistics, and so on, but we'll see a demonstration here if you don't. Let's go back to our problem. That's a problem of bipartite matching as we know it. We know combinatorial algorithms for this. But it turns out that it has an equivalent form. There is another way of asking the perfect matching question that not too many know, and I'll tell you what it is, and this will drive the other algorithm. So here's the other problem. It's called matrix scaling. It goes back to Singhorn and even before Singhorn. So here's the matrix scaling problem. The input is just a single matrix, like the adjacency matrix of a bipartite graph. Okay, just a non-negative matrix. And I remind you what a doubly stochastic matrix is. This is a matrix that row sums are 1 and column sums are 1. That's a doubly stochastic matrix. So I give you a matrix, and I ask you to try to make it doubly stochastic. Maybe it's not doubly stochastic. And of course, I have to tell you what the rules are. So here are the rules. You are allowed to scale the rows by constant, scale the columns by constant. So basically, multiply them by scalars. That's what you are allowed to do. And another way to think about it, you are allowed to multiply from the left and from the right by a diagonal matrix. And the question is whether you can do this so that you get it doubly stochastic. And I want to insist that definition here is that what I mean by doubly stochastic is that row sums and column sums are approximately 1, not exactly 1. So what do I mean by that? You ask whether for every epsilon you can find such diagonal matrices that will make the row sums and column sums up to epsilon from being all 1. Why do I make it this problem and not exact? Because this is exactly the problem that's equivalent to bipartite matching. But I hope the problem is clear. It came up independently of perfect matching, of course. It came up for many, many reasons in this very, very old work. It has roots in numerical analysis, signal processing, and later trying to compute deterministically or approximate deterministically the permanent. And as I mentioned, it's equivalent. So let me write it down. This problem is equivalent to testing whether the permanent of the matrix is positive. Okay, so now that we have this very different formulation, we can ask ourselves, do we want to solve bipartite matching? How can we solve matrix scaling? And it looks sort of non-trivial, right? I mean, we can try it on this example, on the example of this adjacency matrix of this graph. What we want to do, we ask ourselves, of course, here, the row sums and column sums are not all 1, so it's not yet doubly stochastic. And we want to know whether we can scale rows and columns so that it becomes almost doubly stochastic, approximate it arbitrarily well. And it looks like, these constraints conflict, rows and columns, right? And here's the naive or brave or stupid idea which alternating minimization does, this heuristic does. It says, well, do what you can. I mean, at least, certainly, it's easy to make the row sums 1, right? So let's do the row sums 1, and then we'll deal with the columns later, all right? So let's make the row sums 1. How do we do it? We divide by the row sums, and here, so we got it. So, okay, we solved half the problem. Now let's solve the other half. Let's make the column sums 1. We can do that. Of course, we screwed up the row sums, so let's fix them. And let's fix these. And as you see, as you go to the limit, what will happen is basically this. It will not converge. It will alternate like this. You can try it at home slower. It doesn't converge, but on the other hand, you remember the graph I started didn't have a perfect matching, so maybe it's good, I don't know. It's probably worth doing another example. But before doing another example, let me just formalize the algorithm. It's amazingly nice. It's a 2-line algorithm. You don't meet these guys very often, right? I mean, basically, the algorithm alternates, scale rows, scale columns, scale rows, scale columns. Okay? And you never divide by 0. If there was a 0 row, you know that there is no perfect match. So that's the algorithm. So let's run it on and that's what, so alternate, you see the alternate minimization or the alternative structure of the algorithm. You're basically solving some sub-problem of your problem and then move to other parts and reiterate. Let's try it on another example. This is the other graph which did have a perfect matching. And let's see what happens here. So let's scale the rows. That's what happens. Scale the columns. That's what happens. Scale the rows. And maybe you see that the diagonal is increasing and the others are decreasing. And basically, this is a limiting thing. So this does converge. And this graph does have a perfect matching. So like by induction, it works for all. So yeah, let's be more serious about this induction. So this algorithm, as I mentioned, was discovered by Singhorn, and in fact, it was discovered long before Singhorn and was discovered long after Singhorn. And there are various analyses of this. But lucky for us, lucky for me, in a paper from about 20 years ago with Lina Samolnitsky, we also discovered this algorithm independently. And this was in the context of trying to find deterministic approximation for the permanent. Anyway, we discovered it, and we provided an analysis that, as it turned out, as we looked at other papers when we learned about them, was different. And this very different analysis is what will be helpful for us soon with the real problem. So I just want to formalize the algorithm. You run this, and the important thing is it converges not only in the limit, but in fact in polynomial time. You run it n cubed times. Then at the end, let's say you made the row sums 1. You check if the column sums are close to 1, let's say up to 1 over n, in whatever norm you like. And if, if yes, then you say there is a perfect matching. Otherwise, you say no. And what's the analysis of this, this algorithm? It's a very simple analysis. And in fact, it's very natural for any algorithm of this sort because it's sort of a dynamical system, right? You are generating a sequence of matrices, right? And you're trying to argue its properties and convergence. So it's very natural also to pick some kind of potential function, Lyapunov function, whatever you want to call it, progress measure, that will have 3 basic properties. It occurs all over the place in mathematics. And for us, this progress measure will be the permanent itself. And we want the permanent of this sequence of matrices, let's call them AI, is a progress measure. And what properties does it have, this measure? That the permanent of all matrices in the process is at most 1. This is easy because, at every time your matrix is stochastic, the row sums or all column sums are 1, and permanent is never more than the product of row sums. So that's easy. Another thing that's easy, that's important for convergence analysis, is that there's non-trivial progress being made at every step. So you want to say that as long as there's, so they're all, it's all bounded by 1, but if it's below 1, it will jump by at least 1 plus 1 over n at every step if there is room for it to jump. Okay? And this, again, turns out to be a one-line proof using AMGM, arithmetic mean, geometric mean inequality. So that's also easy. So the last thing you need to show is that you don't start too low. And then you say we converge fast. And this is also easy. I mean, in this Boolean matrix, it's obvious. And if it's a matrix with rational entries, you just change what you call n, and will be the binary description. So anyway, all parts are easy. It's immediate. This is the analysis. That's a full analysis of the algorithm. I encourage you to teach it in elementary algorithms class. So this was the, I have to keep my time somehow in check. Started 6:20 something. Okay, so about half. Wait, good. So we now want to generalize. So this is the type of algorithm we want to apply to the real problem. And I stress that the last step is easy because this is going to change. So we've done the baby case where we solve the bipartite matching via matrix scaling. And now we are going to do the real thing, where we solve the non-commutative singularity problem using operator scaling. So I want to tell you about two papers. Gurwitz, immediately after this work I just described, the LSW and this analysis, and then the papers got the algorithm. And the story is, I mean, there'll be three sort of technical slides, but the story is that it's all the same, okay? So it's, except for one important difference, that we need more math. Okay, so here is we are back to the operator scaling problem. Remember, we had a tuple of matrices now, not one. And a symbolic matrix was a linear combination of them. And we asked these questions: is it singular or is it non-commutative singular? And Gurwitz's sort of amazing quantum leap, and it's a pun, or it has at least two meanings, is that he moved to the quantum world. And this is an important message here, that a tuple of matrices or a tensor appear in lots of areas of mathematics, and often, they describe different objects, and different questions are asked about them. So it's another question you can ask about a tuple of matrices. You think of it as, it's again a tuple of matrices, but you think of it as a quantum operator. What is a quantum operator? It's just a linear operator on matrices that takes this tuple and applies, and takes an input P, matrix P, and applies it in this way. So it's a sum of AI P, AI transpose, AI dagger. Okay? It's the most general quantum operation or quantum noise operator that exists in quantum mechanics. It's a very natural object. And now you can ask questions about it. So it's an operator, and you can ask to scale it, like we asked to scale a matrix. And this notion of scaling an operator is also, maybe I should point out, this kind of operator sends PSD matrices to PSD matrices, and that's what they use it in quantum information theory, because these are density matrices describing quantum states. Anyway, you can try to scale this operator, and scaling means something very similar to scaling of a matrix. The formulas are there. It's more or less saying, or exactly saying, that when you evaluate this operator on the identity, you get the identity. When you evaluate it when you evaluate its dual on the identity, you also get the identity. But the way you should think about it is there's row stochastic and column stochastic. It's an exact analog. And this analog, you can see it in the, okay, so let me just point out, why did Gurwitz do that? He wanted to solve this PIT problem, the commutative singularity problem. He actually managed to prove that these two problems, even though they look totally different, are very related. And in fact, if you are doubly stochastic, it means you are commutatively non-singular. But it was not an if and only if, and that's one reason we can not yet solve this problem. But it turns out that was one important starting point for us, was realizing that actually it follows from result of Kohn in the 70s, that these two problems are equivalent, just like matrix scaling and bipartite matching are equivalent. So we might as well solve this scaling problem, operator scaling problem. And we also really know how to solve it, right? So if you think about the way, people, I mean, I'm going to make a cartoon, maybe Scott will, Scott is not a physicist, he will not be mad, but some physicists, here's a cartoon how you quantize a problem. It's really a quantum version of the scaling problem. You take, your vectors go to matrices, matrices go to tensors, you just increase the dimension. L1 goes to L2, and in this sense, exactly, stochastic, doubly stochastic changes. And now if you think about it, the operations of the algorithm or the rules of scaling in the matrix case were just pre and post multiplying by a diagonal matrix, which is a vector. Now you move to invertible matrices. So here's what we'll do. We'll just try to make it row or column stochastic in this general sense by applying left and right linear transformations. And as before, each one of them is easy to do. And so you can alternate them and hope that in the limit it converges. And in fact, that's exactly the algorithm that Gurwitz suggested at the time. You don't have to read it. It looks exactly like the previous algorithm. And not only that, Gurvitz suggested, let's take the LSW analysis and let's see what happens. So the first problem he faced was, well, wait a minute, what is the analog of permanence? What is the progress measure that we are going to take? And he invented one, ingenious one. It's called the capacity. Again, you don't have to read it. It's a very natural functional on operators. But he found one. He discovered that it exactly matches. So if it's not commutatively non-singular, then the capacity is positive, and singular it's 0. So just like with the permanent and the bipartite matching. And he said, let's use this particular measure for the analysis. And he noted that, first step is easy. All these numbers will be the sequence of operators you produce. The capacity will be bounded by 1. It goes by 1 plus 1 over n every step. Same proof, exactly. And then he got to the last point. He just want to say if the capacity is positive, it's non-trivially big, at least exponentially big, so that the number of iterations will be polynomial. And there he got stuck. And somehow it's not as trivial as in the baby case. And that's basically what we did in this work from 4 years ago. We proved this. And I'll tell you more about what's going on, but just as a summary is that you need the following ingredients. Basically, you need invariant theory, which I'll talk about soon. It's really important that the actions of the algorithm, the basic steps, are actually group operations, this pre and post multiplying by matrices, which you can just say, this is it. It's important that they are group operations. The measure that is picked is an invariant, or what's called semi-invariant in invariant theory. And the analysis inherently uses highly non-trivial information about invariant polynomials of this group action. So I'll talk about this in a second. I just want to say what the outcome of this algorithm, sort of keeping the promise from the second slide. Here's we've seen already 2 problems where the input was just a tuple of matrices. On the slide now you see 6 problems. These 6 problems are problems in completely different areas. In each one of these areas, this tuple represents something else. And in each one, the question is very different than the other. And these problems came up naturally long before we went in. And in some of these cases, these questions are absolutely fundamental to the field they are in. And it turns out, and most of it, this information, most of it, you pick it up if you look at the appropriate text. We needed it because we needed it to eventually analyze the algorithm. The first 5 are exactly identical. I don't mean like there is a polynomial time reduction, identical. The answer is yes to one if on a tuple, if and only if it's yes to the other. Okay? And the 6th one is actually a special case. So the algorithm I just showed you actually gives the polynomial time algorithm to all of them. Okay, one fell swoop. Okay, so that's the consequence of the algorithm. Now I want to talk about the analysis and then about what came afterwards. So let me give you, so I started giving, survey talks about invariant theory. I mean, I go around giving invariant theory. But I'll give you just one slide. So invariant theory is about symmetries, group actions, orbits, and invariance. And you know that. I mean, you've seen it maybe, but not called like this. But here are some examples. Here are 2 graphs. You move one to the other. The group action is just renaming, relabeling the vertices, the names of the vertices. Another one, is when you play pool. I mean, the group here is time, right? I mean, you kick the ball, the white ball, and then you let time evolve, and you see how the patterns change. Another one that you maybe know from your childhood is, the group that, you use scissors to cut shapes and move them about and create other shapes. And for each of them, they are invariant. So even though there's something dynamic here, there are things that never change. So for example, in the last example, the area does not change in this process. And in fact, that's the only invariant of this group action. In the case of the physics case, you know, where you learn in high school, that energy and momentum are preserved, and in fact they are the only invariants here in elastic collisions. And in the case of graph isomorphism, maybe Latzi will tell us in a year or two what are the invariants, complete invariants. And for us, we are looking, like you saw in these two examples, we are looking at linear groups of matrices, and they act on vector spaces. And in this case, this invariant theory is extremely developed, and it has an algebraic part, and all invariants are polynomials, and there's a lot of understanding of this, and lots of open questions. And there's a geometric part, which I also hope to show you, that has to do with a non-commutative duality theory that I'll get to soon. Okay, so let's see where you take this to. This was like 4 years ago. I've been giving this talk over these 4 years in versions of 1 hour, 3 hours, 6 hours. We had a whole week workshop, and there's more material, and it gets condensed and condensed. So anyway, I'll condense a lot of into the last 20 minutes. The first thing is to look at what we have and generalize it in the obvious way. So here's what we had, these two examples, matrix scaling and operator scaling. So these are scaling problems. This one thing we can generalize. And we had this algorithm, which was alternate minimization, that we can try to generalize. And I'll remind you, or those who don't know, alternate minimization, as I mentioned, or sometimes called coordinate descent, appears all over the place as a heuristic in lots of non-convex problems in statistics, optimization, learning, and so on. And the structure, in general, it doesn't have to be two parts. Maybe you have a function to optimize or to solve in some way. It can be optimization or sample or something. And it's a function of, let's say, k coordinates. And it's hard to solve it, whatever solve means. But if you fix all but one of the coordinates and just want to optimize the last one, the free one, then it's an easy problem. And if your problem has structure of this type, then you can do alternate minimization. You do this, and you do this, and well, there are many, it's used a lot, and often we don't understand if it converges at all. Often we don't understand even if it converges, whether it's fast, but it's used a lot. And in our case, the setting we are handling is a case where this function is a function of group elements, a group theoretic framework. So natural generalization is to take it in k dimensions and to look at the product of k groups of this type, diagonal or linear invertible matrices acting on the various fibers of in different directions of this tensor. So this is the action. And you don't have to read it. Again, it generalizes what we've seen. And the goal is I'll give you a tensor. Can you scale it? Can you make it, row sums column-wise in all directions be 1, and or the identity matrix or whatever. And this is the uniform version. And there are non-uniform versions. You can ask to have, let's say, in matrix scaling, row sums and column sums be some other particular vectors. So there are non-uniform versions. And putting it here again, it turns out that, well, given what I've shown you already, you'll believe me. I'm not going to give more examples of saying that there are many more applications of this higher dimensional questions in representation theory, in quantum information theory, and so on. And the other thing I want to stress is that these are non-convex problems. The problems here are, the domain is just, groups, products of groups, and they are non-convex problems. And despite this, the same result generalizes. So the main theorem of this subsequent works is that the alternate minimization will get you epsilon close to a scaled position in time, which is polynomial in the description of the object, the tensor, n, and 1 over epsilon. Okay, so this is a very general theorem, and to prove it, you do the same 3-step analysis, only you need to work much harder, and you need more results from invariant theory and representation theory. But this is, you now have this result, and you stare at it and say something is wrong, right? I mean, These are non-convex problems. We are doing the most stupid greedy algorithm, and it converges fast. Something must be going on. So what's going on? You know, why does it happen? You need an explanation. We need an explanation besides just a proof. And more than that, as you'll see, we'll also learn more about just what scaling problems are, and I'll tell you in a second. So that's what we are going to do next. We are going to understand what's happening here. So for this, so the last part is about these topics, non-commutative duality, geodesic convexity, moment maps, and moment polytopes. Do them one by one. And here's a picture again of these two examples that we have. And I remind you that the way we got to them, we had a goal of scaling. And in the analysis, we minimized some potential functions. It was permanent, it was capacity, and it turns out that even the L2 norm is useful to minimize. So now we are going to switch. We are going to look at the optimization problem of minimizing the L2 norm. So let me define it, and in fact, we will generalize further the problem we have, because we are not going to look anymore at just products of groups. We just look at the very general problem of some linear group acting on a vector space. Okay, the most general situation in this side of invariant theory. So again, what will be the goal? It will be an optimization goal. I give you a vector in this vector space, and I ask you, so I drew the orbit of this vector, so everywhere it can move under the group action, okay? And what I'm asking you, the goal, is to compute f of v. F of v is the infimum L2 norm of any vector in the orbit. I just ask you to minimize, to find the lightest vector, let's call it v star, in the orbit of v. And you may ask yourself where it's coming from. Well, it turns out, first of all, invariant theorists are interested in it. In particular, it's very important for them to know even just whether this infimum is zero. Vectors for which this infimum is zero are called the null cone of the action, and it's very important when you try to understand the space of orbits of this group action. Anyway, it's interesting for them, but it's not just interesting. They know a lot about this that's useful to us. So here's what they know, this non-commutative duality. So you can think, this problem of testing whether the limit is zero is sort of a morally an NP question, right? I would give you a sequence of group elements that makes the norm smaller and smaller. This will be like convincing you that it goes to zero. And the question they ask themselves, and that's the duality question, suppose that it's far away from zero, like it never gets close to zero, it's bounded away from zero. Is there a way to demonstrate this? Is there a short proof of the same type? Again, it's a non-convex problem. And nevertheless, they have this duality theorem, very strong duality theorem called Kemp-Ness theorem. It says that if f of v is positive, it's bounded away from zero, it's bounded away from zero, then some other function of the optimal point, of the minimum norm point on the orbit, is zero, is the zero vector. So what is this mu? And that's absolutely fundamental. Mu is called the moment map. I'm not going to define it, but you can just think of a gradient. It's just the distance from zero is positive if the gradient at some non-zero vector is zero. And this should be somehow familiar, at least in the Euclidean case, we know this thing. And in fact, this duality theorem is well, okay, there are several, it says several things, so let me say them one by one. One is, what is the interpretation of mu of something is zero? You can at least try it on the examples of matrix scaling and of operator scaling, and lo and behold, this condition that the gradient is zero is exactly the scaling condition. So scaling problems, even though they had many motivations to arise, they also arise naturally from this duality theory. Having the moment map equals zero is just a scaling condition. So they arise from there. The second thing is that this non-commutative duality is a vast generalization of what we know of as LP duality. LP duality is exactly the special case when the group acting is a commutative group. Okay? And the third thing is that you try to understand, I mean, this really explains why everything works in these algorithms. If this duality is if and only if we stop if we get to a gradient of 0, this is a sort of a local optimal condition, it must be globally optimal. So somehow there is some convexity here. Well, these algorithms work because there is some convexity here. And this convexity is really what's called geodesic convexity, and it extends the normal Euclidean convexity that we know and love to Riemannian manifolds. So in other words, if the problems we talked about are non-convex, only if you think that straight lines are geodesics, but they are not. If you look at the geodesics, then along these geodesics, these functions are convex. And because of that, you have this, basically, it explains intuitively why this very simple greedy algorithm works. And let me now interpret. So given this knowledge, let's interpret the question. We said that scaling problems are problems about, the gradient, this moment map of the optimal vector, of the lightest vector in each orbit. So let's interpret the scaling problems that we had. So we had the uniform scaling problem. It just asks about whether there exists a point in the orbit which has some point where the gradient is 0. And the more general non-uniform scaling problem or marginal problem is a problem just asking whether there is a point in the orbit which a particular vector is a gradient. Okay, so that's a more general problem. So in other words, both problems ask whether somewhere in your orbit of the input given to you, there is another point with a particular gradient. So that makes, it makes sense now to just, maybe it looks strange, but let's look at all the gradients that appear in the orbit. Let's give them a name. So delta of V will be all the vectors that occur as gradients in the orbit or the orbit closure of the input you have. Okay, it's a set. And we are asking membership in this set, right? These are the scaling problems. And here's something that absolutely amazes me. I mean, I'm still blown away, even though I understand, the proof and so on. A sequence of works from, starting in physics and mathematical physics is that these sets are not as weird as you think. They are convex polytopes. Turns out that in all these cases, these sets of vectors in real space turn out to be convex polytopes. And it's sort of amazing because until a couple of years ago, I never met a polytope that was not given either by its extreme points or it's by its facets. Well, you can think about projections, but I mean, they arise out of very, very strange scenarios, and they are all convex polytopes, which is great for us, right? Why is it great? Because we have techniques to solve membership in polytopes. We just have to know that the polytopes we care about are what they call moment polytopes. All right. Okay. I'll just give you a couple of examples of moment polytopes, and just that you'll see how maybe strange they are. So I have two types. I've divided them into two, the first and the second. And basically, the first type are objects that maybe let's run through the first example. So here's it's just a special case of what I described in the previous slides. I give you a symmetric matrix, A, and let's define this set of gradients. It doesn't matter the moment maps, vectors. This is a set of all diagonals of all matrices B that are similar to A, right? Conjugates of A. It's a set of vectors, all these diagonals. Turns out that this is a convex polytope. It's a highly non-trivial effect. I mean, not highly. You can prove it, it's a special case yourself. But and there are others like this where you don't see. So the first type are objects that have no reason to be, at least a priori, neither convex nor linear. Both are non-trivial. On the other hand, in the bottom, I mentioned some polytopes that you know. For example, the Newton polytope of a polynomial is just the convex hull of the exponent vectors of this multivariate polynomial. Okay, so it's certainly a polytope. I define it as a polytope. But there you can ask, what's the group? Where is the group action? Or another one is the Edmonds polytope, right? The polytope of matroid intersection. It also turns out to be a moment polytope. So all these guys are moment polytopes, and we want membership in these polytopes. We have this geodesic convexity. So the last slide, a technical slide I want to tell you about is that, okay, you can start exploring algorithms for this. And in fact, for the very general case, not a product case where alternate minimization helps, but arbitrary group action, arbitrary vector spaces. And you basically know that you have convexity, so you can try to do all the analogs of the things you know from, convex optimization. So you can try, for example, do a first order. So you are trying to solve this problem, so you can do first order methods. I mean, okay, alternate minimization doesn't suggest itself here, but you can do gradient descent. And turns out that you can prove it is very generality, large generality, that you have epsilon convergence in, like we expect in the Euclidean case, in polynomial in 1/epsilon steps. And special cases of this were known, but in this generality, I don't think it was known. And moreover, nothing was known on faster methods. Turns out that getting epsilon close in poly 1/epsilon time for many of these problems is not good enough. You want exponential convergence. And so we developed second-order methods, and they converge in, again, like in second-order methods in usual convex optimization, in polylog epsilon iterations. And of course, like in usual convex optimization, the whole question is what's in this big O? How does it depend on the smoothness of the function? And this turns out, again, to be complicated. It depends on, of course, on the action that you are studying, and you have to do lots of invariant theory and representation theory, but at least the parameters are really clean. The parameters, it ends up there. I mean, there are analogs of these smoothness parameters, and you can calculate them in lots of special cases. So let me finish this technical part, maybe the whole talk, because I'm probably out of time, by just mentioning some obvious conclusions, open problems. I think that it's sort of clear that there's plenty of interaction between algorithms, complexity, and math, and it's growing. The next 2 points are sort of interesting. We started with an algebraic problem, and the solution for it was analytic, which doesn't happen very often. And moreover, to analyze this very analytical continuous algorithm, everybody's happy now with continuous algorithms for combinatorial problems, but the analysis of it goes back to the algebra. And the last thing is that symmetry, we are working with groups. These group questions are really there lots of times, even if you don't see them, like in the bipartite matching case. Natural research directions. Well, I wish that this is useful for combinatorial optimization. We can solve this way, matroid intersection, but I'd like to solve newer problems. I think there's a lot to do in developing geodesic optimization, and what I really want to do is to prove lower bound. So does this method, can you do what you did for, can gradient descent just solve this problem of commutative singularity and relieve us of VP versus VMP? So I guess it's 7:20, I'm out of time, so let me just do this. I wanted to just say that this is just one example of lots and lots of important, of course there's lots of interaction of algorithms and complexity with mathematics, but in particular, considerations that we have for our own reasons turn out to be important, even though they were not maybe designed to be like that, important to various areas of mathematics, and end up solving major open problems. The Cadison Singer is a very good example. All these guys were trying to do is, solve quickly linear systems and build spacifiers. The characterization of primes. It came out to de-randomization, and so on and so forth. So I will not go more into this. There's plenty of examples, and stepping one step higher is, I talked just about mathematics. Very similar things can be said about all the connections with all the other areas. I was going to tell you some things about it, but I'll just skip to the end here. And basically tell you how I view the situation. This is where, it just great theories of different parts of human understanding were initiated by great people. Newton started us on understanding the laws of motion, and we still don't quite understand it well enough. Darwin, similarly with evolution, and Turing, we are just trying to understand the laws of computation, and we are still very, very, very far from understanding them. There's plenty to understand. But lucky for us, I think that he also, put us in a coal mine, so we may be miners, but we are really in a gold mine. And there's plenty to dig for and plenty of great things to discover. And I think what is clear to me, at least, that in a set of problems that's so important internally and externally, and such a demand for the expertise that we are generating by establishing laws of computation, this community should grow. This community should educate everybody outside the community. And the connections, the interconnections that appear and exist and are really foundational to the field, where ideas jump between different areas, is very important. And I think it's very important for this community to remain cohesive, to have a central core. So for the educational part, like Avi mentioned, let me put an ad to my book that hopefully will come out soon. I just sent the final version to the Princeton University last week, and but I keep the copyright, so I can freely advertise it because it will remain free on my website for those who don't want to buy it. And I also hope to improve it if you send me comments for it. Thank you. Questions? Yes.
Okay, so you said that there's this there was this notion of convexity.
Yes, geodesic convexity.
Geodesic convexity. So doesn't that mean we should be able to do something other than alternating for those original problems?
Yes, we can do, and I said that you can do gradient descent.
So what does it look like? Does it look like just applying your R and C together, or?
In that case, in this particular matrix scaling, it looks like applying R and C together, and you have to pick a step size. What's nice about alternating minimization, you don't have to think about step sizes. You optimize this local thing. In this, both the first, second order, you have to think about step sizes, and So I mean, you run into, so you can, everybody who does or knows about, convex optimization knows that they all face these problems. You face the same problems. They are more complicated because this action is not commutative, but it's the same type of problems. And anyway, there's a theory to develop there. I'm sure, I guarantee you it will be beautiful, and I guarantee you it will be useful, but I cannot say exactly to what. Yes?
So in the matrix scaling example, the orbit, you get the polytope is just the matching polytope or something?
the orbit is not the match. The orbit of the group action on a particular, no, it's not. It's the matching polytope. Oh, the moment polytope will be the moment polytope will be the matching. Yeah, absolutely. And I don't know whether the matching polytope of a general non-bipartite graph is a moment polytope. I wish I knew. I tried to prove both ways. Yeah.
One last question.
Well, let's give why one. I mean, have a vote of how many. And anyway, I'm happy to answer any number.
Yeah, so it's just curious, the groups, do they need to have some sort of differential structure?
Yeah, so in this case, all the groups have differential structure. So this is the continuous case. You should think of like matrix groups over the reals or complex numbers. Yeah.
You mentioned something about large fields at the beginning.
Yes, so that was for the operator scaling. So I mentioned that the operator scaling problem, and also the matrix scaling, but that's easy. But the operator scaling problem was found deterministic polynomial time algorithm even for finite fields by a very different algebraic algorithm of Ivanov, Schiao, and Subramanian. And this algorithm you can think as an algebraic analog, a linear algebraic analog of alternating paths. So it goes back, I mean, you can think of it as an extension. This is not known for any of the problems I discussed after that. It's not known, I'm not saying it, yeah, it may be discovered also. This algorithm also uses very heavily invariant theory. More efficient, yeah, so this scaling algorithm for matrix scaling or for operator scaling? For matrix scaling, it's not very efficient. It's not as efficient as the Edmonds-Karp. Yeah, it takes maybe n to the 4th time. I don't know how, I mean, it can be, we have a paper in which there's sort of a better continuous, sort of a second order algorithm for it. I am trying to remember, and Madri and his students have an algorithm, similar algorithm for this. And yes, it's continuous and it's much more efficient, but I cannot tell you exactly the complexity. Yes. I think the number of iterations, is close to linear. Yeah. 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 Oh, Madhu. Yeah.
In the L2 minimization problem that you mentioned, I mean, what happens if you consider norms other than L2? I mean, for zero testing, they're the same. But,
Yes.
For the minimization problem, is there still some sort of a duality theory?
So I don't know. L2 is special, but it's very natural. And it turns out that it's essentially equivalent. If you know the L2, you know the capacity. And you know, even though these look like much more complex measures. It's a good question. I don't know what happens with other norms. The invariant theories, as far as I know, just minimize the L2 norm. You just want to know whether it goes to 0. They don't. It's not about the norm. Just want to know whether it goes to 0. Yeah.